Hello students, welcome to EPG Pathshala. I am Dr. Maimuna Akhtar from School of Pharmaceutical Education and Research, Jamia Hamdard. Today we are going to talk on module Analysis of Environmental Pollutants by Atomic Absorption Spectrophotometry under the paper Atomic Absorption Spectroscopy. After completing this module, you should be able to understand what is environmental pollution and what are its sources, the kind of heavy metals present in environment, various methods of analysis, analytical procedures for determination of lead in water, soil and air, and analytical procedure for determination of arsenic in water, soil and air. So what is environmental pollution? What do you understand by what environmental pollution? First, what is environment? So environment means water, air and soil which surrounds us. So the pollution means majorly the pollution of water, air and soil. The quality of water as described by agencies in terms of concentration and state. State means the dissolved or particulate matter of some or all the organic and inorganic materials present in the water together with certain physical characters of water. In this section, we'll be focusing on analysis of some heavy metals in water, air and solution by using atomic absorption spectroscopy. So heavy metals like lead, nickel, cadmium, magnesium, chromium, etc. We all know they are very dangerous and not good for health, beyond certain limits especially, and are responsible for number of diseases. It is reported that they cause systemic toxicity, specifically neurotoxicity, phytotoxicity, nephrotoxicity, teratogenic effect. Phytotoxicity means the toxicity to the fetus, that is that baby within the fetus only. Teratogenicity means which results in the limbs, dysfunction of the limbs, that the limbs are not formed in the womb. So it is very serious problem. So if anybody is exposed to heavy metals, we need to be very careful. It is also reported that they induce impairment and dysfunctioning of blood and cardiovascular system, endocrine system, eliminative pathways, colon, kidney, liver, skin. Not only those, energy production pathways are not spared, not even gastrointestinal and enzymatic pathways are spared from the heavy metal toxicity. Immune system, nervous system, peripheral or central, reproductive or urinary, all suffer lethal effects due to presence of heavy metals in man or animals, which is a result of pollution. Source of heavy metals in environment. There can be varied source of metals in environment. We'll discuss one by one their source into environment. Lead, there are two sources. Industrial source that comes from the burning of coals and roasting of minerals like iron pyrite, dolomite or alumina, and domestic use of solid fuels, for example coal, biomass, agriculture waste, etc. Paints, ceramic glaze, cosmetics and folk remedies, drinking water, etc. all can be source of lead in environment. Arsenic, naturally it comes from sediments containing arsenic bearing minerals. It may also be leached and percolated from areas rich in arsenic in soil. It can be due to anthropogenic activity like agrochemicals, wood preservatives, mineral processing, industrial source, acid mine drainage, burning of fossil fuels. The source of nickel can be wind-blown dust, weathering of rocks and soil, volcanic emissions, forest fires, and vegetation. Due to anthropogenic activity like combustion of coal, diesel oil, and fuel oil, incineration of waste and sewage may be some other sources of nickel in environment. Mercury majorly comes from chloralkali industries. coal-fired plants like steel industries, thermal power plants, cement plants, pulp and paper industry, medical instruments, plastic industry, electrical appliances, pharmaceutical and other agriculture products. Ferromanganese minerals such as biotite, mica, and amphiboles contain large amount of manganese and can be the primary source of manganese in the environment. Crustal rocks is another source of manganese. Ocean spray, forest fires, vegetation, volcanic activity are some other major sources of manganese in atmosphere. Marine system is one of the natural source of selenium in the atmosphere. Other anthropogenic activities which result in selenium in environment are anti-dandruff, antifungal pharmaceuticals, agriculture use of phosphate fertilizers, application of sewage sludge and manure to land, use of selenium containing fungicides and pesticides. Methods of analysis for determination of heavy metals in environment. There are a number of methods that have been used for determination of metals in environment. To name few, flame atomic absorption spectrometry, atomic emission spectroscopy, graphite furnace atomic absorption spectrometry, inductively coupled plasma mass spectrometry, X-ray fluorescence spectroscopy, isotope dilution mass spectrometry, electrothermal atomic absorption spectrometry, and other methods like nuclear magnetic resonance spectroscopy, near IR, inductively coupled plasma optical emission spectroscopy. This is a representation of single beam atomic absorption spectrometer. It contains a source of light with a chopper, that means selector of wavelength, a sample cell, and flame or furnace, followed by a monochromator which selects the wavelength of the emitted light, then fed to the detector which analyzes the light, a detector which may be a photomultiplier tube or other CCDs, then the recorder and readouts. Among the various methods of analysis of pollutants, atomic absorption spectroscopy is one of the reliable method for analysis of lead in the sample. So method used generally depends upon the type of sample and sample source. Sample source means whether you have acquired it from soil, water or air. All the analytical methods based on atomic absorption spectroscopy differ in atomization method or source of excitation and detectors employed in the instrument. The major difference in the procedure comes from the preparation of sample, because like you can have limited number of atomization method, you can have limited source of excitation and detectors, but the samples can be of different nature from different sources, so the variation or difference between the examination or analysis comes from the preparation of the sample. For example, a sample from environment needs to be prepared and handled differently from a sample which is obtained from biological source. The method described are related to samples obtained from environment and is described as per the protocols of the manufacturer, that is Perkin-Elmer, unless otherwise mentioned. Since we are talking of atomic absorption spectrometer, that means we are using an instrument. And instrumental techniques have one limitation, that you have to follow the protocol of the manufacturer to obtain reliable and precise results. This slide shows you the standard atomic absorption conditions for determination of lead. The lead can be identified or determined at number of wavelengths starting from 283 through 364.0 nanometers with a cell of 0.7 nanometers. The relative noise levels from 0.4 to 1.8, characteristic concentration of 0.4 to 67.0 milligram per liter, and characteristic concentration check of 0 to 3000 milligrams per liter with a linear range of 20 milligrams per liter. The recommended flame is air acetylene oxidizing. Data obtained with standard nebulizer. The data presented is with data obtained with standard nebulizer and flow spoiler. The sensitivity can be increased 2 to 3 times if the same is operated with high sensitivity nebulizers. The characteristic concentration that can be obtained with nitrous oxide and acetylene flame at 283.5 nanometers is 2.7 milligram per liter. This slide shows you a workflow for determination of element in a sample by atomic absorption spectroscopy. To start the protocol, the first sample is collected and it is solubilized or digested depending upon the source of the sample. In the instrument, the background corrections are made and the lamp source of light is chosen and prepared properly for analysis. The instrument is adjusted and aligned and the flame is lit and the flow and oxidant flow are regulated. To the desired, a standard is run and calibration curve is constructed, and from this calibration curve, coming to analysis of lead in water. First thing required is sample, and you need to be very cautious while sampling because you cannot just sample at one place and tell that yes, this is the amount of lead and water is polluted or not polluted. You need to have sample from locations that are representative of the water source. For example, storage facilities, treatment plants, distribution network, and points of use. Then preparation of solution. For any analysis, you need to prepare sample, you need to prepare standard solutions. So how standard solutions and sample solutions are prepared? First, standard solution of lead. A lead 1 milligram per ml solution is prepared by dissolving lead metal in nitric acid of 6 molar strength, which is lead free, and diluting it with water. Dilutions from this stock solutions are prepared just before use. You can prepare a stock solution and then use this stock solution to prepare different dilutions. The sample under test is prepared in the similar manner. That means if you are using nitric acid in your standard preparation, you have to use nitric acid only. You cannot use anything else for preparation of your sample. The apparatus and procedure. Apparatus, we already know that we are using atomic absorption spectrometer. That means we use atomic absorption spectrophotometer and some volumetric flasks, micropipettes, and the procedure is as per the manufacturer. As I mentioned, in instrumental techniques, the limitation is you have to proceed according to the instructions given by the manufacturer. The reagents required for determination of lead in water include methyl isobutyl ketone, diethyl dithiocarbamate solution, which is made by dissolving 20 grams of diethyl dithiocarbamate acid sodium salt in 380 ml of deionized water, filtered by a 0.5 micron millipore filter, and then extracted with methyl isobutyl ketone and phthalate buffer. Hydrochloric acid, sodium hydroxide of 1 molar strength, standard solution of lead, dilute stock standard solution of lead of desired strength, standard containing 10, 25, 50, 75 and 100 microgram per liter of element. In this case, lead is prepared and acidified to maintain pH between 1 to 2 and treated as described under sample preparation. The sample preparation is done as per the source of sample. In this case, we have water sample. So water is collected by using Van Dorn type sampler and filter. 200 ml of this is filtered through 0.45 micron millipore filter. The filter is washed with 100 ml of deionized water immediately prior to the filtration. The filtrate obtained is acidified with conc HCl and 100 ml of the acidified water sample is transferred to 250 ml conical flask. To this is added phthalate buffer and pH is adjusted to 3.6 plus minus 0.1. To this solution, DDC solution and MIBK solution is added in separating funnel and shaken vigorously. It is then allowed to separate into two different layers and a layer of MIBK is collected. After the collection of the prepared sample, it is analyzed. The analysis of this organic layer for lead in this case is element of interest versus similarly extracted standard and reagent blank. The use of routine procedure described by the manufacturer manual is opted. The calculation is done by preparing a working curve from the extracted standard and blank, and concentration of the element of interest is directly read from the curve. We all know lead is abundantly present in soil also. So we need to analyze lead in soil as well. And in this case, the sample treatment is different as compared to your sample treatment in case of lead estimation in water. So first sample is digested. Digestion means you treat it with various acids and extract lead from it. So what we need to do is we weigh an amount of soil sample and place it in a 100 ml beaker. The sample quantity should be less than 2.5 grams per analysis. The water is added to the sample and concentrated nitric acid is added. It is then mixed with a glass rod and covered with non-ribbon glass watch with concave up. Concave means you have to the depth on the upper side. Heat the sample on a hot plate until refluxing. Refluxing means you heat till it boils and the water starts condensing coming back. So allow it to cool and add 5 ml of the nitric acid again and start refluxing again. So after cooling again, the HCl and water are added and the mixture is refluxed again with occasional stirring. It is first heated slowly. The heating is kept at 3 first. So as soon as it starts refluxing, the heating is reduced to 1. Finally, the solution is filtered through a qualitative filter paper into a volumetric flask and the beaker is held upside down in a tilted position at an angle so that you can add some water and that comes into the funnel so that any residue that is stuck onto the beaker comes or is rinsed with the water so that no solid is attached or you can say sticking to the beaker. But do not overshoot the mark. Analysis of lead in soil. For their analysis, a standard preparation of lead stock solution is done by dissolving 0.1598 grams of lead nitrate into 1 liter volumetric flask containing 1% nitric acid. This stock solution contains 100 parts per million of lead. The use of stock solution to make standard containing nominally 15, 10, 5, 2 and 1 parts per million weighed by volume of lead and 100 ml of each of the standard solution containing these strength is prepared. 1 part per million lead is usually used as standard and it is used for 2 reasons. One, the absorbance of this solution will be plotted on a calibration curve and second, its standard deviation will be used to determine the atomic absorption spectrometer's limitation in detection and quantitation. The analysis and calculation of lead in soil. The analysis of the element of interest is done in similar fashion as done for the extracted standard and reagent blank. The use of routine procedure as described by the manufacturer is followed. A working curve is prepared from the extracted standard and blank and the concentration of the lead is determined directly from the calibration curve. The analysis of lead in air involves sampling at a certain flow rate using certain cellulose member. The sampler uses a filter of 0.8 micromolar cellulose ester membrane and it is collected at a rate of 1 to 4 liter per minute. The minimum volume of sample required is 200 liter at the rate of 0.05 milligrams per mole and maximum is 1500 liter. The blanks 2 to 10 field blanks per set is required. Accuracy range of the instrument is 0.13 to 0.4 milligrams per cubic meter to 0.15 to 1.7 milligrams per cubic in case of fume atomic absorption. Biasing of minus 3.1% can be observed. Overall precision is 0.072 to 0.068 and accuracy is plus minus 17.6. For measurements The ashing is done by using concentrated nitric acid 6 ml, 30% of peroxide 1 ml at 140 degrees centigrade. That means you take the sample, add nitric acid and peroxide, heat it to 140 degrees centigrade. Dry it, then dilute the residual by nitric acid 10% to 10 ml. Feed to the spectrometer with a flame of air acetylene at a wavelength of 283.3 nanometers. Do the corrections, background corrections with D2 and H2 lamp or Zeeman effect. The calibration curve of the lead is prepared in 10% nitric acid with a range of 10 to 200 micromolar per sample. The estimated loss on drying is 2.6 microgram per sample and the precision is 0.03. The reagent used for the estimation of lead in air includes nitric acid, 10% nitric acid volume by volume, hydrogen peroxide 30%. Calibration stock solution required is 1000 microgram per ml of lead and which can be obtained commercially or it can be prepared by dissolving 1 gram of lead metal in minimum volume of 1 plus 1 HCl and dilute HCl. It is then stored in polyethylene bottles and is stable for 1 year. From this, the working solutions can be prepared at the time of experiment. And the sample used is for air, compressed and filter. Acetylene is used. Required distilled or deionized water. The equipments used are sampler for collection of air sample, a cellulose ester filter 0.8 millipore size, 37 millimeter diameter in a cassette filter holder. Personal sampling pump 1 to 4 liter per minute with flexible connecting tubing. Atomic absorption spectrometer with an air acetylene burner head and background correction. Lead hollow cathode lamp. Regulator 2-stage for air and acetylene. Beakers, volumetric flasks, assorted volumetric pipettes, hot plates, surface temperature, etc. are other things which are required for analysis. The sample are prepared in the following manner. The sample and the blank are transferred in a clean beaker and concentrated nitric acid 30% hydrogen peroxide is added. It is then covered with the watch glass and start the reagent blanks at this step. It is then heated to 140 degree centigrade and the volume is reduced to about 0.5 ml. The same is repeated twice so that a average of 3 readings can be done. So when sample is dry, rinse the watch glass and wall of the beaker with 10% nitric acid. Allow the solution to evaporate to dryness. Cool each beaker and dissolve the residue in concentrated nitric acid. The solution is transferred quantitatively to a 10 ml volumetric flask and diluted to volume with distilled water. The recording of the lead emission is done according to the specifications provided by the manufacturer. The sample is aspirated, sample and standard and blank is aspirated in the system, absorbance and emission is recorded and measurements are done. The calculations corresponding to the concentration of the sample microgram per ml of lead is calculated from the observed absorbance and average media blank from the calibration graph. Using the solution volume of the sample and media blank, the concentration air volume sampled is calculated by equation. Analysis of arsenic. The analysis of arsenic in environment is very important aspect since arsenic is very toxic in nature. This slide shows you the standard atomic absorption conditions for arsenic. It can be determined at 3 wavelengths 193.7, 189.0, 197.2 nanometers with a slit of 0.7 nanometers and relative noise of 0.95 to 1.8. The characteristic concentration ranges from 0.78 to 2 milligrams per liter and characteristic concentration check from 40 to 90 milligram per liter. The linear range is 100 to 250 milligram per liter. The recommended flame is air acetylene reducing. The data obtained in the table is with standard nebulizer and flow spoiler, and by using high sensitivity nebulizer or impact bead, sensitivity can be increased 2 to 3 times. The characteristic concentration with nitrous oxide and acetylene flame at 193.7 nanometers is 1.4 milligrams per liter. Stock solution of arsenic, 1000 milligrams per liter. It is prepared by dissolving 1.320 grams of arsenic oxide in 25 ml of 20% weight by volume potassium hydroxide solution. It is neutralized with sulfuric acid 20% volume by volume to phenolphthalein endpoint and diluted up to 1 liter with 1% volume by volume sulfuric acid. The flame used in determination of arsenic, the air acetylene flame absorbs or scatters more than 60% of the light source radiation at 193.7 nanometers of arsenic line. Flame absorption is reduced with the use of the nitrous oxide acetylene flame. Although sensitivity is also reduced, so use of background correction is recommended as it will correct for flame absorption and thus improve the signal to noise ratio. Light source. Number of light source can be used for determination of arsenic. However, hollow cathode tube and EDL source are very suitable for arsenic determination. EDL is more suitable because it has more intense and provides better performance and long life in determination of arsenic. A sample with high total salt content, that is greater than 1%, can produce non-specific absorption at 193.7 nanometer even when the metal is absent. So it is therefore advisable to use background corrections. For analysis of arsenic in water, a standard solution of arsenic 0 to 75 parts per million is required, which is prepared by dissolving an appropriate amount of anhydrous arsenic trioxide in 0.1 molar sodium hydroxide. The water samples are collected from the representative places like wells, public water supplies, treatment plants, and bottled waters, etc. A 50 ml aliquot is directly delivered by a pipette man into Perkin-Elmer 4000 graphite furnace atomic absorption spectrometer fitted with an HGA 400 temperature programmer. The slit width set at 0.7 nanometer and the optimal wavelength of 193.7 nanometer with a potential applied to the hollow cathode tube 18 millivolt is optimum condition for measuring arsenic in water. The furnace assembly is purged with argon at a flow rate of 50 to 200 milliliters per minute. The flow rate of 50 milliliter per minute is optimal flow rate. The temperature programming composed of a drying, charring and atomization, and the solvent is removed from the sample matrix through vaporization and the time and temperature is determined. The sample is heated to 130 degrees centigrade for 50 seconds under a stream of argon 50 milliliter per minute. The rapid solvent boiling is avoided because that destroys the sample. The organic material is decomposed or vaporized during the charring step by heating at 1700 degrees centigrade for 30 seconds and removed under a stream of argon 50 milliliter per minute. To reduce sputtering, the temperature was ramped over a period of 2 seconds during these first two heating steps. The third and final step in the heating process atomizes the sample to analysis, and this is done by heating the sample to 2700 degrees centigrade for 10 seconds. The gas flow is slowed or stopped before the rapid increase in temperature to ensure the analyte remains in the graphite tube. Otherwise, no absorption will be observed. In the atomization step, the elements of interest atomizes to gaseous state and an absorbance reading is obtained. To ensure complete removal of the last sample, the graphite furnace is manually fired to 2700 degrees centigrade for 5 seconds and a blank is run to 0, the instrument, before running the next sample. This slide shows the schematic representation of three-step temperature program. First, the temperature is such that the sample is dried, increased in such a manner that the charring happens, and finally it is increased to a level where the sample is atomized and where absorbance of the energy takes place. This is the typical representation used in graphite furnace atomic absorption spectrum. Since arsenic is also present in soil, so estimation of arsenic in soil is also done. and this is done by extraction of arsenic from sediment and followed by analysis of arsenic by atomic absorption spectroscopy. So if you want to analyze arsenic in soil, two steps have to be followed. First, you need to extract the arsenic from the sediment or soil, and then the extraction or extracted material is analyzed for arsenic. Extraction of arsenic from sediment or soil. The extraction involves wet ashing of the sample by using any of the acids like sulfuric acid, nitric acid, peroxide, hydrochloric acid, boric acid, or hydrogen fluoride, or any of their combination. Some of the methods used by government and researchers are summarized in Table 5. The extracted solution are then analyzed for amount of arsenic present by number of analytical instruments like graphite furnace atomic absorption spectrometer, inductively coupled plasma mass spectrometry, or inductively coupled plasma atomic emission spectrometry. Atomic absorption spectroscopy is not generally preferred for arsenic detection due to poor detection limits, that is less than 1 milligram per liter, because the limitation of arsenic in any sample is very low, it's in parts per million. So therefore atomic absorption spectroscopy is generally not preferred. So once the decision is made, the sample is analyzed by the instrument as per the instructions of the manufacturer. The standard protocol we know has to be followed as per the manufacturer, and it is given in Table 4. This shows you extraction and analysis method for total arsenic in soil and sediments. The first column shows the reference, or you can say source, like United States Environmental Protection Agency mentions a protocol. Similarly, another scientist, A. Marin, has given a standard protocol for extraction method analysis and recovery. According to US EPA, for extraction, a mixture of sulfuric acid and nitric acid is used. The amendments were done in 1904, wherein in place of sulfuric acid, hydrogen peroxide can be used. And in 96 amendments, the nitric acid with HCl can be used with an analyzed method of graphite furnace or ICP-MS. The recovery is 100 to 102%. So according to A. Marin, you can use a mixture of 3 solvents: nitric acid, sulfuric acid, perchloric acid. And analysis method can be atomic absorption spectroscopy. Recovery is 96 plus minus 3%. By using HCl and nitric acid combination as extraction method, 74% plus minus 1% has been shown as recovery of the sample. So students, by now you must have learned about environment, the environment pollution, the causes for the environment pollution, various sources of the environmental pollution, and different methods of determination of lead and arsenic in water, air, and soil using standard protocols. Thank you.